slides are okay. I'm going to do a little bit of scrambling. You know how I like to kind of give you, there will be homework that's going to be due, and I usually kind of give you hints about the homework, so we're going to kind of do that together. But we did one, we're going to take a look at the gas law problem that we did in lecture on Monday. Okay. Oops, sorry. But one of the things you probably want to put on your review sheet is PV equals nRT, and then know how to use it. I kind of tease because in physics there's a lot of formulas, and this is a formula where you just plug in what P is, what V is equal to, what N is equal to. R is always a constant. Okay, that's, for us, we're going to use 0.082058 liters atmospheres per mole Kelvin. There are different values of R, I think I mentioned, because they have different units. Okay. But like in physics, basically, of these 5 different letters that mean a different variable, one will be missing. Okay. So we did an example, and just to kind of remind you, this is the example that we did. Okay. It says, what is the gas pressure? So we were after P. Okay. And then it goes ahead and gives the volume. Bless you. We had to fix the volume. The volume needs to be in liters, so we had to get it from mils to liters. It gave us N. Remember, moles is N in PV equals nRT. And the temperature, a lot of times they'll give it in Celsius, which is an awesome scale, but it needs to be in Kelvin. So we added 273 to that. It's 273.15 more specifically. So this is how we did the problem. Okay. Oops. Just kind of going through these slides. And you can actually go about this a couple different ways. You can either rearrange PV equals nRT for P, like we did here. I kind of like that. Or you can just kind of plop in your volume, your moles, which is N, your R, okay, and your T, which is in Kelvin. You can plop those in, or you can rearrange the ideal gas law equation for P, which we're trying to solve for. And then we plugged them in. Oops, sorry. And this is what we left with on Monday. Okay, so we plugged in the value for N. Okay, we plugged in the value for R. Let's see, so N is here, R is here, T is here, and V is here. Okay, so we just kind of plugged them in, so it's not too bad. But if on your exam on Monday, if you have one of these and it's one of the ones at the end of the, where you have to show your work, remember you're going to have some problems at the end of your test, your final, where you have to show your work, and there's some problems, multiple choice, where you don't have to show any work. I'll have scratch paper. Or you can write on your test booklet too. Okay, but you'd have to use units. And the cool thing about which you will, is units, remember we said of moles cancel, units of Kelvin cancel, units of liters cancel, and we're left with units of atmospheres, which is what we were after when we were going for pressure. So let's do another example. And then actually, what I'm going to do for your 10 extra credit points is you guys are going to do one of your 2 homework problems for 10 extra credit points, and then the other homework problem you need to turn in when you come Friday for lecture. Okay. So when I do these, sometimes I draw a box with the little particles in them, you know, meaning gas particles, but sometimes I just draw out what I need to know, P, V, N, and T. Okay? So just even looking at it, you know it has to do with gases. Carbon dioxide, that's a gas, right? And then I kind of start pulling from the problem what I know. So right away it says what volume, so I'm going to put a question mark next to my volume. What volume? Okay. Now, this is classic. Notice it gives us 0.20 grams of carbon dioxide. What we're going to do in this problem is we're going to go from grams to moles. I'll put an N there. Actually, we're going to get our N down here where it says N. I'm going to say from 0.20 grams of CO2. We can get moles, right, from grams. We're going to have to use the periodic table and knock out the molar mass of CO2 first, and then use it to get from grams to moles. If we go on, it also gives us pressure. Okay, so pressure is equal to 732 millimeters of mercury. And if that's throwing up some flags, you're right. That pressure is fine, but in order to use that value for R, your pressure has to be in units of atmospheres. So remember that homework where you did some conversion from millimeters of mercury to atmospheres? That's what you're going to have to do. We're going to have to get to ATMs, not where you get money out of like an automated teller machine, okay, but units of atmospheres. I guess the other thing, this is just kind of, I really am a firm believer in just kind of diagramming problems, kind of pulling out information. The temperature is 22.0 degrees Celsius. We can't use that like that. We need to add 273.15 units to get it to Kelvin temperature. So that's kind of how we're going to knock this one out. So one of the things I'm going to do early on is I'm going to take PV is equal to nRT, and I'm going to isolate volume by itself. Okay, and to get volume by itself, it looks like if I divide both sides by P. Does that look right?
Yeah.
Okay, I think so too. So divide it by P, divided by P. So here in a minute, you're going to see something like this. The volume we're trying to solve for is nRT divided by P. A really common mistake in these is just to kind of mess up the algebra. And I've done it before too. But if you mess up the algebra, your units won't come out right. We need units of what? Liters. So let's see how this works. So the R value we'll use is that 0.082058. R has units of liters and atmospheres in the numerator, moles and Kelvin in the denominator. Okay. So I already kind of told you that we're going to get N, we're going to get moles from grams of CO2. We're going to have to clean up our Celsius temperature to get it Kelvins. And this last bullet down here, our pressure needs to be in atmospheres. It's in millimeters of mercury. Go figure. Okay, so we're going to have to fix that. We can do that. The ones that you're going to do for your homework and probably the one on the test, you won't have to probably mess with millimeters of mercury going to atmospheres and that sort of thing. So this is the isolating for volume because that's what we're after. PV equals nRT, or V is equal to nRT over P. So like I said, we're going to have to go from those grams of CO2 to moles to get our N. So in order to go from grams to moles, we need the molar mass of CO2. So we take 12.01 plus 2 times the decimal number for carbon, 16.00. So the molar mass that we're going to use is 44.01 grams per mole. So it's kind of a side problem. If we take the mass of the carbon dioxide over 1, we use the flipped version of the molar mass. 1 mole of CO2 per 44.01 grams of CO2. Rounded to 2 decimals, we know what N is now. So our N is 0.0045 moles. Pretty slick. A few other things to clean up before we plug into V is equal to nRT over P. So here's cleaning up our temperature. The temperature was in Celsius. And actually on your note card or on your, I guess you guys have a full sheet of paper, which can be, like I take a cardstock. I take some pretty color paper and I would, maybe print off a periodic table with the names. And I would write on that periodic table things like, we talked about how 1A forms a +1 cation. I do that stuff on my periodic table. Bring with you. I know it's a different unit. But I would also put, how do you get from Celsius to Kelvin? I would put degrees Celsius plus 273.15 is equal to Kelvin. Okay, so that's going to be our T term. And our P term, remember, we have to clean up the whole millimeters of mercury to atmospheres. also on my note card, just in case you needed it, I don't think you will, but this is a common thing where they give you millimeters of mercury, and our R value actually is in pressure units of atmospheres. I probably would put this on my note card. I put 1 atmosphere, and you've seen this before, is exactly equal to 760 mmHg, millimeters of mercury. I would put that on my note card too, because actually that's what we're using right there. I mean, you can put on your note card whatever you want to. You could put like happy thoughts, you could put stickers, you could put a picture of your kid, you know, that would work. Okay. Okay. So now by my estimation, we're ready to plug in N, and of course R we know, and T we've got fixed, and P we've got fixed. So this whole course, when you work physical science problems, when you work any science problems, you really should include units, even if you're plugging into a formula like this. So if we take a look at the units, okay, we have, of course, N is 0.0045 moles times R, which is 0.082058. Units of R are liters atmospheres per mole Kelvin. In the numerator, we have the last term is the temperature, 295.2 Kelvin. And that's all divided by the pressure, 0.963 atmospheres. So the beauty of getting in the habit of including your units is you have confidence. We know for volume we're after liters. Well, let's see if we get liters. Moles have canceled. Units of Kelvin have canceled here. Units of atmosphere have canceled here. Okay, we're left with units of liters. That's awesome. 2 significant figures, you should get 0.11 liters. So that's using PV is equal to nRT when you're solving for V. We solved for P before. So let's take a look at the one that you're going to do for extra credit. So like I said, this lists 59, 61, and 64. And one of these, let's do 59 as extra credit. So I'll pull it up. You can pull it up too. 59. Okay, so this is only due Friday. Okay. And this one you did is EC. All right. So, on to just a little bit more. More. Okay. And actually what you're going to see is I'm skipping one part of this. So go ahead and go to part 3. And you'll skip, I think you'll find it right after the assignment slide. So hopefully it looks like this. Okay, good. All right, so now when we go to lab tomorrow, I should have brought it, but in lab there's this beach ball looking thing, and it's got the different colored, kind of looks like an apple you might cut into wedges. And that's like my little beach ball to go with this slide. This is so cool. One of the things I said about your box of gases, I don't care if it's nitrogen, I don't care if it's oxygen, I don't care if it's water vapor, I don't care whatever sort of gas it is, it has this relationship, pressure times the volume is equal to number of moles times R times the temperature. So all gases have this sort of thing going on, okay, that regardless of the gas, okay, if your gas is at what we call standard temperature and pressure, I guess I should back up a little bit. When we work gas law problems, standard temperature is 0 Celsius. Okay, standard temperature 0 Celsius. Standard pressure is 1 atmosphere. Okay, exactly 1 atmosphere. And exactly 0 Celsius, which is kind of weird because you know there's uncertainty there. Okay, so that's standard temperature and pressure, STP, for gases. It's different for other sort of chemistry problems, for gas problems. So here's the deal. let me go ahead and draw PV equals nRT. PV is equal to nRT. Almost seems like you could have a rap going on with that. Okay, so if we set the pressure is 1 atmosphere, exactly, and if we set the temperature is 273.15 Kelvin, which is 0 Celsius, right? And let's go ahead, do one more thing. Let's going to say that we're only going to talk about exactly 1 mole of substance. Okay, so N is 1 mole, R is a constant. We're going with standard temperature of 273.15 Kelvin. We're going with standard pressure of exactly 1 atmosphere. The only thing, I'll put constant there. Your big R is a constant. The only thing unknown is your volume. So here's the cool thing about all gases. If you have exactly 1.000 moles of gas, and it's at 0 Celsius, and if it's at 1 atmosphere, its volume will be 22.414. I mean, there's no magic there. We're just actually setting the 3 of those 4 variables in the ideal gas law equation. We're setting N, we're setting T, and we're setting P. So the volume is 22.414 liters. And so back to my beach ball, okay? So my beach ball, it contains 22.414 liters, which you're like, man, that's a lot. But if you figure liters about a quart, okay, so that's just about, and it takes 4 quarts to a gallon, that's a little over 5 gallons. That's not that much. So anyway, so let's take a look at a few problems, okay? And to work this, we're going to use PV equals nRT. This is going to feel very similar to what we already did today, okay? So what volume will 45.0 grams of nitrogen gas occupy at standard temperature and pressure? I'm going to show you how similar this is to what we've been working. I'm going to go ahead, P is equal to, V is equal to, N is equal to, T is equal to, all right? So our pressure, just like I said a minute ago, if it's standard pressure, our P is 1.000, how many zeros you want, atmosphere. Okay. Let's go ahead and finish that standard stuff. If it's standard temperature, guess what? It's 273.15 Kelvin. We'll just go ahead and go with the Kelvin temperature, not mess with the 0 Celsius. Okay. Let's see, what else does this problem? Oh yeah, this is kind of like the problem we did with the carbon dioxide. Okay, the moles right here, they don't give us moles, but we can get moles from 45.0 grams of N2. We can get to moles. And that's exactly what we're going to do. So, I mean, it just starts to flesh out the problem. So, actually, the one thing we don't have pulled information-wise is the volume, and actually, that's what we're after. What is the volume? So that's kind of what it looks like. So actually, we're going to rearrange PV equals nRT just like we did before, right? So it's going to be very similar, very similar. This is the first thing, we're going to knock out the grams of N2 to moles of N2 using the molar mass. So its decimal number is 14.01. So don't forget to show this on the last part of your comprehensive final exam if you need a molar mass for anything. So if we go ahead and start with the 45.0 grams of N2 gas that was given, use the flipped version of the molar mass, so grams will cancel, we'll be left with moles. We round to, what, 3 significant figures. That's going to be our N term. Oh. I forgot. Oh, forget. Let's go back. Okay, so end it there. Let's see, 45. This problem is working it another way, but 45 divided by 28.02 Okay, so N is 3 sig figs, 1.61. Okay. So now we're ready to plug in. Let's see. So let's plug in. I'm going to assume that you guys are good with this. V is equal to nRT over P. Okay. So in this case, V is equal to that 1.61 moles times 0.082058 liters atmospheres per mole Kelvin. The temperature is 273.15 Kelvin, all divided by 1.00 atmospheres. Unit-wise, our moles have canceled like they've done before. Our units of Kelvin cancel. Our units of atmosphere cancel. We're left with units of liters. So, I got, let's see, 3 sig figs. I got 36.0.
3.1, when then we just round up, I have an 8 after the 0.
You got an 8 after the 0?
36.08676975.
Yeah,
Okay, I used an unrounded value, so tell me again. So it'd be 36.1.
1.
Okay, thank you. Perfect. Are we good with that? I think so too. This is just working a different way. Okay. So this one will also be due. Only 83, so let's take a look at that one right quick. I think you'll do fine with it though. They're fun, really, they're fun. Other than you have 10 billion other things to do. I know it's the end of the semester. So let's just go with the first two, 83A and B. Okay? And then one more type of problem. So the last type of problem is, I just think they're all so fun. But it's called the combined gas law. And what the combined gas law counts on is literally, when you work these problems, you'll have a situation A, okay, where you're given certain information about the gas. That same gas then, you'll be given a situation B. Okay, actually we're going to call this state 1, and this is going to be called state 2. So if we rearrange PV equals nRT, and if assuming situation 1, state 1, and situation 2, state 2. Assuming between those two boxes of gases, it's the same gas, the point here is I have the same number of moles. So I'm not going to take any moles out or add any moles. Okay, so if N is constant, I'm going to go ahead and put it over here with my R, which is also constant. Okay, in this particular case, in this particular type of problem, then pressure times volume over temperature needs to be constant between those two boxes. Not to say that we aren't monkeying with the pressure, or monkeying with the volume, or monkeying with the temperature, but multiplied by each other and divided by temperature, it needs to be constant. So here's what it looks like. Here's my state 1 and my state 2. Okay, can you see the little subscripts? The subscripts mean 1 means state 1, the subscripts 2 mean state 2. Basically, you have a confined gas, you're not monkeying with N, and this is the relationship you have going on. P1 V1 over T1, this one you might could put on your note card too, I'm not sure, is equal to P2 V2 over T2. Okay. So let's see what this looks like. Okay. Now I'm not going to diagram it here because it's diagrammed on the next slide, but literally I know this looks like a really wordy problem, but But if you read it a few times, you'll start to see the state 1 and the state 2. It says an ideal gas, originally state 1, at 12 degrees Celsius. We're going to have to put that in units of Kelvin. Okay. Also gives the pressure of that original state in millimeters of mercury, but actually we can keep it in millimeters of mercury. Okay. And it also gives the volume of that original state. Those first three numbers is the original state. It says, what if the temperature is changed? So that's my state 2. Okay. It doesn't tell me what the new temperature is, but it says when the temperature is changed, now it gives me a different volume. That's at 46.7 milliliters. And it gives me the different pressure. That's that 353 millimeters of mercury. So there, you know how story problems like this, a lot of times they'll read, they won't read the same, but all of this stuff is state 1, and all of this stuff is state 2. Okay, that's part of your problem in working a problem. So the question mark, actually, do you guys get this? I think it's here. Okay, I've called state 1 initial and state 2 final, which is fine. Okay, but the thing we're trying to get to is T2. Okay, so I think I talked about the crisscross sort of, I talked about flattening out an equation. So one of the things we worked on earlier, yesterday, on Monday, we said if I'm trying to get to T2, probably what I would do is what I call flatten this thing out. And flattening it out, I'm basically going to take this and multiply by each other. So when I flatten it out, I have P1 V1 T2 is equal to P2 V2 T1. Okay, that's my flattening out. I like it flattened out because now, if I'm after T2, now it's a lot easier. So do you buy this? To get T2 by itself, I need to divide both sides by P1 V1. Okay, so rewriting that, now I've got T2 is equal to, and I'm going to nest them like this. I'm actually going to kind of line them up like this. T2 is equal to P2 P1 and also V2 over V1 times T1. All I did was kind of break it out. You could have, in the numerator, gone P2 V2 T1 divided by, in the denominator, P1 V1 also. It's the same thing. But the cool thing about this is, I know when we use PV equals nRT, we said your pressure has to be in units of atmospheres. I know we said that, and that is totally true, because R, right? I don't have any R here. When I work this problem, I'm going to leave pressure in millimeters of mercury. I'm going to leave volume in milliliters. Okay? But my temperature does need to be in units of Kelvin. So that just kind of takes a little bit of work off the front end. So here's our little fixing of the temperature. Okay, this one, instead of adding 273.15, I've just added 273 because I figure I only knew the Celsius temperature to the nearest ones anyway, so it's all like that same thing. So that's going to be our T term. T1. All right. So this is my kind of rearranging. This is what I got in the previous slide. T2 is equal to P2 over P1 times V2 over V1 times T1. It's the same thing. Combined gas law has two states, initial and final, or state 1 and state 2. N is constant. All right, here we go. So T2 is equal to 353 millimeters of mercury over 322 millimeters of mercury times 46.7 milliliters over 33.5 milliliters times 285K. So the units really kind of pop out at you what cancels doing it this way. Like I said, this is why you can leave whatever units of atmospheres and whatever units of whatever units of pressure, whatever units of volume. Rounding to 3 significant figures, you should get a temperature of 436 Kelvin. We've done so much with gases this semester. There's a good chance you're going to see. I'll do something different for the final, that I'll just throw in one for extra credit. Extra credit on the final? Do you do that? What the heck? It's been an extra credit sort of semester. Okay? But remember, it'll be any problem you see at the end of the test, you have to show all of your work to get full credit. Okay? But it's extra credit, but still you should show all your work. Okay? Okay. Oh yeah. So I don't even know if the original problem asked for this, but if you wanted to fix up your Kelvin temperature, to knock it back down into Celsius, what you do is instead of adding 273, you subtract 273. So that actually would give us our Celsius temperature.
Yeah, and actually, what must the new temperature be in Celsius?
Okay,
Yep.
it does ask that. On any test, including your final you take Monday, if you have any questions about the test, you can come up and ask for clarification. You guys know, and if I can't answer, I'll let you know, but, okay. So, well, the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. That whole thing assumes N is constant. Your two states, the number of moles aren't changing. Well, what if, in addition to N being constant, what if temperature is constant? If temperature is constant, check this out. Basically, that T term in the denominator goes away. Okay, so this is the combined gas law, where N and T is constant. We've got a few other ones. What if the volume is held constant? Okay, if the volume is held constant, then that V term goes away. So you have P1 over T1 is equal to P2 over T2. And the last scenario is if your pressure is constant. If in addition to your moles, your pressure is also constant, then your V1 over T1 is equal to V2 over T2. Kind of makes sense. I love the combined gas law. So let's go ahead and I'm going to change this up. This will be the third problem that's due, because did I only have 2 other problems?
Yeah.
Okay, so this is the third problem that's due. We're not going to do this first one. Let's just do, and we'll take a look at it together. Let's do this one. So 55 is out too. We have 3 problems. So let's take a look at 1153 right quick, and we'll call it a day. Where did it go? Oh, yeah. That's not right. Must be right here. Okay, so this is the one that's going to be due. Okay, and it's fun. I'm not going to, just to kind of get the ball rolling, I'm going to remind you that I would go P1, V1, T1, P2, V2, T2, and start pulling out stuff. Okay. What is the volume of the balloon? To me, you're solving for that. Yep. Okay, and it's an odd number, so you can get the answers at the back of the book. Okay, any questions? Okay, very good. So we'll see you tomorrow in lab.
Yay. Gas lab, blow stuff up. No.